customers in North and South America. And so today I'm just going to give you a quick overview of our activities in nanolithography, and also something we're less known for, but which is becoming more and more important, reverse engineering. So we're very well known for our product line for nanolithography. These are electron beam lithography systems and also focused ion beam lithography systems. And for 3 decades, we've been supplying add-on pattern generators for existing SEMs and FIBs, and we continue with that activity today. What we're less known for are our reverse engineering products, and I'll tell you what these are in a moment. Actually, these are large area scanning electron microscopes. And I'll tell you towards the end of the presentation what these are capable for. But this is called the chip scanner, and it's used for reverse engineering. So I'm going to be talking about lithography and also reverse engineering. So let me start with lithography. By definition, the lithography transfers information into a material. And so we start with a GDS2 CAD file, and we end up transferring that information into a material, and at the nanometer length scale. So these are a few hundred nanometers diameter circles. So that's the basic definition for lithography. The kind of lithography that we're doing is vector scanning lithography using focused beams of electrons and ions. So here the focused beam of electrons is writing a pattern on a wafer. However, when it reaches the limited writing field of the electron beam, a laser interferometer stage is used to move the wafer below the writing field to an accurate precision of nanometers. And so a careful beam control working together with stage positioning allows for stitching together of very large patterns over nanoscale patterns over large areas. And so, again, our systems are not really serving manufacturing, because writing with Gaussian beams is a very slow process. However, it's very flexible. You can do a wide variety of cutting-edge research with vector scanning lithography systems. And here's our customer, Konstantin Novolov and Novozolov and Andrei Geim. They use their electron beam lithography to make the first devices, and continue to be active in making devices in graphene. And of course, they're the discoverers of graphene, which is why they got the Nobel Prize in Physics in 2010. So we have a wide variety of products in nanolithography. I'm not going to go through all of these, I just don't have the time. However, I will touch on the Pioneer, the Wraith 152, a special zero stitching error writing mode, which is special to our company, and as well as the ion line. So the Pioneer is our most affordable solution for electron beam lithography. It's also the perfect EBL-SEM hybrid. Remember, you can take an SEM and convert it into a lithography system. Well, here we have what we call the perfect EBL-SEM hybrid. So it's capable of very high resolution lithography. These are 20 nanometer lines. And remember, these can be stitched together over large areas. So very high density lithography using field emission, electron source technology. It's also capable of overlay. And overlay is a very important process, especially in nanolithography, when you need to build up devices layer by layer. Here's an excellent example of that. Perhaps you can see below the oxide layer there's gold split rings, and then there's a silicon oxide layer, and then another layer of gold split rings. This is a careful overlay process. And especially for optical metamaterials, it's really important to control material dimensions down to the scale of 10 nanometers and below. Otherwise, the optical performance will change drastically, and you'll see a few examples of that. So again, this is a 100 nanometer scale bar, so these are sub 100 nanometer structures that are being carefully overlaid above one another for these metamaterial tasks. So the Pioneer system, like all vector scanning lithography systems, is capable of stitching. Microsoft is very powerful, but it is not perfect. But if you know where the bugs are, then you should be able to make things work. So this is the Pioneer's laser interferometer stage. It's moving at the scale of a 2 nanometer precision. And so with the laser stage, you're able to stitch together large patterns. So waveguides are often very long and need to be stitched together using the laser interferometer stage. And this is a 200 nanometer scale bar. You see the slots are varying ever so slightly, just by a few tens of nanometers. But the performance of each slotted device, very, very drastic difference in performance. So this basically says, our research community is telling nanolithography companies like us that they need to control materials down to the scale of below 10 nanometers. The Pioneer also features a full rotate tilt capability, and so this is what really makes it the perfect SEM EBL hybrid system. And so this is a field emission SEM as well, so you're able to capture very high quality SEM images. Okay, so I don't have time to talk about the E-Line Plus. However, let me get into a high-performance electron beam lithography system. This is the Wraith 152. And essentially, this is our most robust and highest performance for traditional electron beam lithography system. And it's capable of handling 8-inch wafers. So the idea here is that you want to do sub-25 nanometer lithography with the flexibility of having electrons. But you want to do this over a wafer scale. And so here we have a case where we have a very complex GDS2 design, and for Infineon, our Wraith 150 system 10 years ago was used to place sub-20 nanometer gates for these transistors. So again, the Wraith 150 is our highest performance system. In fact, it does hold the record for resolution in electron beam lithography, as demonstrated by our customers at MIT. So now I'm going to get into a special writing strategy. It's called zero stitching error lithography. So remember, let's just take a step back to vector scanning lithography, where we're stitching together patterns over large areas. But at this boundary right here, there's going to be stitching errors. 3 sigma of about 40 nanometers is the specification for our tools. So stitching errors are a concern, because if you have 40 nanometer 3 sigma stitching errors and you're dealing in photonics, you don't really like that. In fact, Okay, so when you have stitching errors, and I'm going to show you some really horrific examples of stitching errors now. These are some waveguide devices. These are extremely bad examples of stitching. There are even stitching errors that you cannot observe in the SEM that give photonics researchers problems. And that is why people are actively, even with $5 million instruments, getting together and trying to address the problems with stitching errors in their instruments and publishing papers, even in 2012, on this very problem. At Wraith, we have a solution. It's called Fixed Beam Moving Stage. The product name is tracks. It's like riding railroad tracks, if you will, over very large areas. So here you just focus the beam and you move the stage underneath, and you write over very large areas with virtually zero stitching errors because it's a continuous writing mode. So here we have a spiral waveguide device written with electron beam lithography. The scale bar here is 100 microns. The magnification is 31x. So we couldn't even capture the entire spiral waveguide in the field of view. It is 1 meter long. Not millimeters, it's 1 meter long, and it was written in 30 minutes, and of course with zero stitching errors. So our field size would typically be, let's say, 100 microns. So imagine breaking up this into a bunch of stitch fields. You would see stitching errors everywhere, but with tracks, you can write it continuously. Some examples of these are 2 millimeter long waveguides, just to give you an idea of what the photonics research community is asking for. This is a coupling light from a fiber into the nano world using a grating coupler, tapered structure down into a nano photonic waveguide. And so just some of the results. All these structures were, especially the extended structures, and even these structures here were written with fixed beam moving stage lithography. And then our customer, our first FBMS customer at the University of Alberta, writing 3 millimeter long waveguides. So anyway, it's a real problem that Wraith has a unique solution for. The ion line is a focused ion beam lithography instrument, and focused ion beam lithography complements electron beam lithography in the following way. Electron beam lithography only exposes resist in nanofabrication, whereas focused ion beam lithography can address many different steps along the nanofabrication process. And in this sense, it serves as a complement to electron beam lithography. It does not replace electron beam lithography. And so focused ion beam lithography can do 3-dimensional milling. This is a microfluidic channel that was stitched together over a millimeter length using focused ion beam lithography. A couple of other examples. Wafer level nanopores. This is a 6-inch wafer, maybe a 4-inch wafer. We also taken the process up to 6-inch wafers as well. And here you see nano devices, and the focused ion beam lithography system is very capable of putting nanopores in each device. And this whole process just took a few hours. This cannot be done with electron beam lithography, by the way. In fact, all of the examples that I'm showing you cannot be done with electron beam lithography. So these nanopores are used for single biomolecule detection. And here we have the Imperial College of London is already looking at 100 nucleotide long DNA from E. coli. And these are basically single transit events of this DNA molecule going through these nanopores. So this is a wafer level task. This is a typical focused ion beam system cannot operate at the wafer level like this. This is why we built the lithography instrument. And then 2 more slides for reverse engineering. And recall that not only is Wraith active in nanolithography, but we're also seeing a good demand for reverse engineering. And this is a growing business for us. So we have, what is reverse engineering? Well, recall in lithography, you're taking information and you're transferring it into a material. In reverse engineering, you're basically doing the opposite. You're starting with an unknown chip, and you want to essentially record using an SEM. You want to record SEM images over very large areas in order to ultimately extract the GDS2 file, and then we have customers using proprietary solutions to even produce the net list and even the schematic. So here's an example of the chip scanner 152 system. This system is, by our customers, is typically being used for 7 to 10 days, continuously recording images at up to 50,000 pixels by 50,000 pixels for each image. The laser interferometer stage can stitch together each image, so you get very good stitching at the image borders. And so this is a very, very powerful way of collecting images. And then what our customers do is they go down to meta layer 2 and they do the same thing all over again. Since they have the laser interferometer stage, they have basically overlay registration between one layer of SEM images and another underlying layer of SEM images. And so this is a very demanding but important task. Our customers are using this Wraith 152 system to look at obsolete chips, to check for counterfeiting, and also for other defense purposes at technologies below 64 nanometers. And so thank you very much for your attention. And I'd be happy to talk to anybody. We're here today. Tomorrow's the exhibit. What time is the exhibit close?
12.
12? Okay. So I'm here. Thank you.